My name is Abir Biswas, and I'm a professor at the Evergreen State College in Olympia, Washington. I'm a geologist by training, so I've been teaching class in geology and in soils. And this past year, I had the great fortune to work with Jan Ward, and we collaborated together as she produced her work, The Book of Knowledge, Bound, Unbounded. So as you can see from this slide, a lot of my work was focused on Mount St. Helens. And in this picture, you can see the different impacts from the little pink and purple area that was the eruption of Mount St. Helens in 1980. And a lot of my work was out on the right side where that yellow star is, where we were sampling an area called the tephra fall zone, which was where a lot of ash had fallen, impacting forests and impacting soils. And when Jen and I spoke and collaborated on Zoom and on the phone for 9 months, we spent a lot of time talking about Mount St. Helens as being a catastrophic event. It was a volcanic eruption. And that catastrophic event led to some rebirth of the mountain, right? In terms of changing, but the vegetation recovered. Many of the ecosystems are recovering and have recovered. And in spite of that catastrophe, we scientists have been able to use this system to study, at least in my case, right, long-term mercury input. So mercury is a toxic trace metal. And so looking at the input of toxic trace metals to ecosystems, and also working with collaborators, primarily biologists and ecologists, looking at long-term vegetation recovery and the change of the composition of the vegetation in these sites. So you might wonder where the mercury is coming from that's entering these sites, right? So the mercury is a toxic trace metal, but it's a natural toxic trace metal. And so in that sense, it's been around forever. And this natural toxic trace metal has entered these sites in two main ways. One, it was associated with the original ash that fell to these sites. So when it rained down as Mount St. Helens erupted, that material brought some mercury that was bound inside those rocks. Okay. The other possibility is that it's being, and in fact, the other pathway is that it's being added to these sites and a little bit lost also all the time because it's natural. And so it's found naturally in the rain. And so it's being deposited in that way. And then also mercury has a gas phase. And in that gas phase, it can enter into the stomata of the needles and the foliage. And so it can be added to the foliage or absorbed the outside of these needles and then fall down when the foliage falls down and be added to the soil, right? So these two pathways by which the natural mercury is added to these systems. Here are a couple of pictures of our, in this case, collaborators and students. And the bottom left is a picture of us working out in the field this summer, all you can see wearing masks due to COVID. And in the top left picture, of course, you can see an old growth tree from one of our sites. And these are pictures of our students and one of our collaborators, Dr. Joe Antos, and another collaborator, I'm sorry, I didn't have a picture, Dr. Don Zobel, and students of mine, and another collaborator, Dr. Dylan Fisher, who's the one in the orange vest in the bottom left corner. And so Jan and I would talk about research in geology, research in biology, working with collaborators, working with students, the role of researchers and scientists in gaining new knowledge. And it kept coming back to biology and geology and the mountain and these ecosystems. I wanted to say a couple of things about my work in particular. So on the left side, you can see really big trees, and that's characteristic of the old growth sites. And on the right side, you can see some smaller trees, and that was characteristic of some of the sites that had been clear cut. And so the really old sites had accumulated a lot of organic matter and had accumulated more mercury. And the relatively younger sites had thinner soils, had less organic matter, and had less mercury. And again, this was part of repeated discussions with Jan around geology and biology and Mount St. Helens as a system. And you can see at the very bottom, it was important to note that there are very different vegetation at the two systems, and also that they'd been changing through time. And that was part of the long-term research that we've been doing at Mount St. Helens. So I want to talk about our findings. And so a little bit of background first, right? So we're looking at some old growth sites, and these old growth sites are about 600 years old. And we're looking at some clear cut sites. Those clear cut sites were just clear cut right before the 1980 eruption, and the trees were covered. And so they're 35 to 40 years old. Okay. And so at both of these sites, we're using an approach that our collaborators set up in 1980. So in 1980, just after the eruption, our collaborators, Dr. Don Zobel and Dr. Joe Antos, were the two who first set it up. And since then, I've been working with Dr. Dylan Fisher. And the three of them are biologists, particularly plant ecologists and botanists. And I'm collaborating with them on this work, right? Vegetation is really their expertise. And so in 1980, Joe and Don set up a grid of 1 square meter plots. And so there's about 600 1 square meter plots spread out at a series of different sites. And we've been going back to them every 5 years to study the change in the plants that are present. And so it's the species of the plants that are present and the relative numbers. And so when you return every 5 years since 1980, we're able to see trends in changes of the plant species composition at these sites. Now, we applied that same design of a grid of 1 meter square plots to the clear cut sites that are seen on the right side. And so we started those about a little over 5 years ago, and we returned this past year. And so we've been there twice. And it's that same principle of 1 square meter plots. And inside that 1 square meter, we're looking at the plants that are present. Okay. And the big picture is that you have very different plants between the old growth sites and the clear cut sites. And they have been changing differently since 1980. Okay. Now, in addition to looking at the vegetation, right, my expertise is more in soils. And so right adjacent to those vegetation plots, we collected soil cores. And so we collected soil cores right next to the places where we've been looking at vegetation. And we are therefore able to connect the biology and the geology at these sites. And they're definitely linked in the context of mercury, and I'll explain a little bit. But the notion now is where we had a grid of vegetation plots, we also have a grid of soil cores. And so we're able to understand the landscape scale because we have a bunch of soil cores that we collected in the field. And we're able to understand that there's a new organic matter that's been added since 1980, and then the ash and the tephra that was deposited in 1980. And that's what we collected, we brought back to the lab, and we prepared them for mercury analysis. And so we analyzed them for mercury by heating them up and measuring them using a methodology called cold vapor atomic absorption spectroscopy. And so we have an instrument at Evergreen, and my students did a lot of this work with me. In fact, they did a lot of the work. I showed them how to do it. They did a lot of the work. Okay. Now, as I said, the biology and the geology are connected, and here's the idea. So again, in the picture on the left side, the old growth forests, right? As you'll note, I wrote organic rich soils and more mercury storage in the soils. And there's 2 reasons that are driving this. So the first thing is, as I said, it should be the same amount of mercury being added to both sites via deposition, so atmospheric deposition. Okay, but the gas phase notion, right, the idea that the mercury could, in the gas phase, enter into the stomata or even sort of, or of the needles, or bind to the outside of the needles, right? You can see that there's a lot more of a canopy at the old growth site. And so the old growth site is able to trap more mercury out of the atmosphere than the clear cut site. And therefore the old growth sites have more mercury added to the soil than the clear cut sites. And so in addition to having more added, the second thing is this. The old growth sites, again, because there's more of a canopy and there's more material just falling down, they have a thicker layer of organic matter on the soil surface at the old growth sites. And that layer of organic matter binds to the mercury. And so it helps to retain the mercury at the site. And so those are the 2 pathways, right, by which the mercury, and there ends up being more mercury at the old growth sites than at the clear cut sites. And so there's a couple of things that I want to say. First off, the levels of mercury that we see here are consistent with other forested sites in the United States. A little bit more at the old growth site, a little bit less at the clear cut site. But these numbers are not considered to be terribly dangerous. It's consistent with other forest sites, and they're not particularly polluted. They're just normal forest sites. And so you might wonder, well, what are we trying to do here? And what we're trying to do is to understand what controls the distribution of toxic trace metals on the landscape, And we want to understand essentially how different kinds of trees and different kinds of canopies are driving how mercury is either retained in different systems or distributed between different systems. So these discussions led to Jan producing her excellent work, the Book of Knowledge, Bound, Unbounded. And you can see reflections of the mountain and geology and biology and plants and trees in her work. And in a way that I can't really put my finger on, she did a fantastic job of capturing the fact that this collaboration had been done in 2020 during a time of COVID. I'm deeply appreciative to have had the chance to work with Jan, and I'm so impressed at the work that she produced. I am gratified to have had the chance to work with her on this Science Stories project, and I hope that you enjoy her work as much as I enjoyed it.